How many 8s do we have?
4.
4. How many 9s?
2.
2 9s. And how many 10s? 1. So this is a line plot. So that's very different than a line graph. Again, it's something that may be new to us, but it's basically a very easy graph for kids to make. So it tends to be found in the lower elementary grades. Okay? Are we cool with this? All right. Grocery store keeps track of apples that get spoiled each month. The pictograph below charts the data. How many apples were spoiled in March? Okay, so they're tracking how many are spoiled. So help me with this. In January, how many apples were spoiled? 10. Okay, 10 for each apple. Okay. How many were spoiled in February? 40. What was the question? Was March. So how many were spoiled in March? 25. Okay, so reading a pictograph is as simple as converting the scale to actual numbers. Okay? We cool with this? Nothing too difficult right now, right? Okay. Number 4. We have a line plot, and now we have a question. So this is ramping it up just a little bit. Here's the question. The question is, consider the following line plot for test scores. So this is some kind of a test that went from 30 to 50, and a variety of test scores there. What percentage of the test scores were above 43? Okay, so to do percentage, I'm going to have to do a couple of things, right? What are some of the things I've got to do?
Got to have the whole total.
Got to figure out how many we have total, how many test scores are there total, and then we have to figure out how many are above 43, right? Okay, so how many scores do we have total? 26? Okay, so the total is 26. And above 43. Now, what's interesting about this is we actually have a 43. So technically, if I'm above 43, do I count this number?
No.
No. Okay, so I'm going to count everything to the right of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 10 out of, so larger than 43 is 10. We want to do a fraction, 10 over 26, and what do we get for a percentage?
38.
What is it?
38.
38. So we can see a little less than half or above. Now here's the next question. Estimate the average scores. Well, remember that, how do we do estimates of average scores when we have something like this? Any kind of a graph like this?
Well, you just take the one in the middle, right?
No, that's the median, would be the one in the middle. You'd add them up and divide, but on a graph, what would be the mean, the average? Remember when we did it with histogram? It's the seesaw. If we had a seesaw with all these sort of equal weighing people on the seesaw at these different spots, where would we put the fulcrum to balance it? Where would be the support to balance it? So notice you've got a cluster over here, you've got a cluster over here, but you've got a real heavy, you got 6 people parked right here on the end. There's 5 people parked on the other end. So it's probably going to be just a little bit, if you think this is actually the middle, like about 40, it's probably going to be about 40, maybe a little less. So you would estimate, and so it says estimate the average and explain your average. You would talk about the contributions for both ends. There's a big weight on each end. Those are pretty far out. These are pretty close. It's probably around 40 or 41. and that would be your estimate. If there were a lot of heavy ones on one side, you would move the average a little bit to consider that, just like you would do on a seesaw. Okay, so that's the logic. So it's really the word you want to put in your notes is it's the balance point. It's the balance point that balances all these contributions. Okay, and it's not always the very center. It could be a little bit to the right, a little bit to the left, depending on how the piles are going. Okay, so I don't want you to actually add them up. Well, I mean, you could check your answer by adding up and dividing by 26, but I'm actually just saying I want you to get that concept of what visually it looks like for something to be the mean. Okay, so let me give you another example, just so that we have that. If I had a curve that looked like this, the balance point is going to be right in the middle. Okay, if I had a curve that looked like this, you see how it's kind of smushed one way? The balance point wouldn't be in the middle. It actually would be over here somewhere. Okay? Because it's being pulled to the right by all this pile of data that's to the right. And the same thing as if I had it lumped up the other direction. Instead of being in the middle, it actually would be this direction. The balance point would be right in here somewhere. Okay? By the way, this is called symmetric. This is called skewed, and it's actually the opposite of what a lot of people think. Skewed left, because wherever the tail is, that's the direction of the skewness. So it's skewed left. So this is symmetrical. And so the mean would be at the very center in a symmetrical graph. When it's skewed to the left, actually the mean is drawn towards the pile that's on the right. And if it's skewed right, that's where the tail is, then the mean is actually slid a little bit over to the left of the center because it's a pile. And this has confused stat students for 1,000 years, or 500 years, okay? Why they call this skewed left and skewed right. I always remember it's the opposite of what you would think. This is where all the data is clumped over here to the right, so it's skewed the other direction. That's how I remember it. It's kind of backwards, the label, okay? Now, the last question on this one is, what percentage, or what is the median of the test scores? Now, I'm going to put the screen up for just a second so I can actually sort of look at this and draw right on it. Okay. Trying not to draw on the screen. One of these days I'm going to draw on the screen. But you remember how we did medians if we actually had the numbers. We line them up from smallest to largest and find the middle one, and if we need to take an average, we take an average. Well, you can do exactly the same thing when you have a line plot. Okay? I can start crossing off smallest, largest, smallest, largest, small, large, small, large, small, large. I got one more large. I got to take this one out. I got the next one, this one, this one, this one, this one. So for every one below the median, I'm going to take one off above the median. I'm going left, right, left, right, left, right. So the two center scores are 40. Notice I didn't have to do any calculations. All I had to do was read where the median was. Okay, so I go all the way to the left, all the way to the right. I keep knocking off items until I get to the two center ones. If they were different numbers, I'd have to average the two. If they're the same number, in this case, like they're all in the same stack, it's going to be 40. Okay, so everybody see how to do a median in a display. Okay, yes? Is that clear? Okay. All right. Now, next question. Do a histogram. All right. So what I want you to do is actually take a moment, copy down the data, and see if you pull out your notes and do a histogram here. Okay. Let me put the screen down so you can see it. I'll read the data off if that makes it easier for you, or you can read it yourself. I'll just read it across so that you have it if you want to just jot down what I'm saying. 29, 35, 16, 32, 25, 82, 17, 29, 53, 26, halfway there, okay, 45, 9, 35, 12, 35, 27, 16, 33, 47, 25. I'll read them again just so you can double check that you have them right. 29, 35, 16, 32, 25, 82, 17, 29, 53, 26, 45, 9, 35, 12, 35, 27, 16, 33, 47, and 25. So take out your notes on how to do a histogram and see if you can do it. How many people need a copy of this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. While you're working on the histogram, I'm going to go print out some copies. I'll be right back.
So it's divided by 6. It's divided by what? 5. My bad.
Who need a copy? Got one? Russ needs a copy? Hey, how's you doing that test?
Oh, you're right.
Anybody else?
Do you have any extras?
What's that?
Do you have any extras?
No. I'm sorry, I guess I didn't count.
Yeah, I didn't raise my hand.
You need me to cover?
Sure.
Okay. Yeah. Histogram. All right. Okay, somebody help me with the histogram. What's step one?
Find the largest and lowest number.
So we're finding the range, right? For number one. So histogram. Step one is find the range, right? What's the range? 82 minus 9, which is what? 73. Then what do we do? If we add 1, okay. So so it's going to be 74, okay. And then we divide by how many classes? 5. So what do we get for the answer there?
14.8.
14.8, and our rule is we always round down. So our classes are the following, right? We have our minimum score is 9. We add 14 to it, and the top of the range is going to be what? 23. We skip 1, and then we add 14, and we get 38. 39, we add 14 and we get 53. Add 1, we get 54. This is 68. And then 69, 83. Okay? So those are the intervals. And then we have to count up the frequency for each. So this interval, freak. Okay? And what do we get for the first frequency? 5. So just simply count them up. How many do we have for the second one? 11. Third one? 3. Fourth one? 0. And last one? 1. Okay? So our largest frequency is 11. So when I'm doing my graph, I want to show a scale that at least will include 11, okay? So I'm going to do 5, 10, 15, going to do little hash marks, okay? And then I'm going to do the classes. I've got 5 classes, so I'm going to put them in here, 1, 2, 3, 4, 5, okay? Let me put the screen up so that you can see what I'm doing. So we have 5 classes. And we put the numbers in here so anybody that's reading it can tell what they're looking at. 9 to 23. Jump over 24 to 38. Jump over 39 to 53. When I say jump over, I'm going past the line there. 54 to 68. And the wider you make that, the easier that'll be on people's eyes. So I scrunched it a little bit so I could fit it in there. But if you need to spread it out so that people can see it easily, that's fine. Okay. And then I'm just going to make bars equal to those frequencies, right? So the first bar is 5 units tall. They're touching because these are intervals. There's no gaps between them. This is not discrete data. This is one interval leading into another. So we have 5. The next one's 11. So we make a line here at 11. And that tower is going to be 11 units tall. Okay. 3 is the next one. So make a tower at 3. The next one's 0, so I'm just going to do a flatliner right here. Not going to do anything, and no height to that. Okay? And then 1 is right here. One of the major advantages of a histogram is you can tell the shape of and it works great with large data sets, okay? And so I can tell right away what the shape of the distribution is. Is it, you have choice A, B, and C. Is it symmetric? Is it skewed right or skewed left? Symmetric is choice A. Choice B is skewed right. Choice C is skewed left. Okay, how many vote for A? It's symmetric. Good. Okay. How many vote for choice B, skewed right? Okay. How many vote for choice C, skewed left? How many are not going to vote? Okay. All right. And you're honest. Okay. It actually is skewed right because where the tail is. So if you have a clump on this side and a tail going in the other direction, the direction of the tail is the skewness, so it's skewed right. Is everybody cool with this? Okay. James packed fruit that was being donated to a local food bank. He packed up so many of each. The question is to make a circle graph and make sure the central angle for each section of the pie graph is listed, okay, is given, calculated, and list each one, okay? So in a circle graph, the first step we have to do is figure out these various angles. So let's go back through and see if we can remember the steps, okay? First of all, we have 25 apples. We have 37 oranges. We have 22 pears. We have 13 peaches. And we have 9 plums. Okay, so what's my first step? Add them up. What'd you get when you added them all up?
106.
106. Okay, once I add them all up, what's my next step? Okay, so we're going to take 25 over 106, right? And what is it's going to be a little less than 25% because that's a little bit more than 100. What did you get? 24%. Excellent. Okay, 37 divided by 106. We're going to get 36%. 35%. 22 divided by 106. Hold on. 21%?
Yes.
Okay. 13 divided by 106, did we get 12%?
Yep.
Okay. And 9 over 106, is that 8%?
8.
Okay. If we add them all up, should get something close to 100%. That seem right? Okay. Now, I can actually, percents are okay, but if I actually turn these into decimals, I can actually, on a calculator, just simply multiply them by 360. Okay? So, it's okay to do them in percents, okay? But if I actually change it to a decimal, now in my calculator, I can just simply multiply that by 360, right? So I've got 24%, which is 0.24. I'm going to multiply that by 360, and what do I get?
86.
86 degrees. So right away, 86, how big is that?
A little less than a quarter.
A little less than a right angle, right? So you can figure what a corner looks like, just a little shy of that, okay? 35% of 360 is what?
126.
126. So is that going to be bigger or smaller than a right angle? It's going to be bigger, about a third of a circle. Okay, and bless you. 21% of 360?
76.
76, so it's going to be less than 90, a little bit smaller than that. 12% of 360?
43.
43? when we have a right angle and if I split it in half, how many degrees is that?
40.
45, so this is going to be just a little less than a pizza slice, right? Okay? I'm trying to give you some visuals so you have just a picture of roughly how much each of these degrees are. And 8% of 360?
29.
29%, okay? So if this is a corner, 90 degrees, I slice it in half, that's 45 degrees, that's a pizza slice, right? Okay? If I cut it in half again, what kind of a pizza slice is that? That's pizza slice for a kiddie party, okay? So the old trick was they brought the pizza with 8 pieces, and then you slice them in half once again, and you have 16. That's about a little bit more than that, okay? Just to give you an idea what it looks like, because now we don't have a computer do it. We have to actually put this into a graph, okay? So you can start wherever you want to. We can start at the top here. This first one, apples, is a little less than 90. So I'm going to go, 90's right there, a little less than 90, and this is going to be apples. And it's a nice touch to actually put how many apples there are so the reader can figure out it's not just a little wedge, but there's 25 apples in there. Okay? The next one's 126, which is more than 90 degrees, but it's a significant amount more, so it's about a third of a circle, and this is oranges. And there's 37 of them. Okay? The next one is pears. It's a little less than 90. 90 would be here. It's a little wedge, and it's a little less than 90. Pears. Okay, and that's 22. Then we have peaches. It's about a kitty slice. Or no, actually a slice of pizza. So this is peaches. If you do it kind of correctly, that last wedge is going to be a kitty slice, and that's plums, and there's 9. Okay? And the finishing touches on this is to put now that we've calculated those angles, to actually put those angles into the diagram. Okay, so I've got 86 degrees. Okay, this is for our purposes. When I say calculate each angle and put it in there, now you're putting it in there. 126, 76 degrees, 43 degrees, and 29 degrees. Okay, so the final pie chart or circle graph has, this is fruit donations to the food bank. Okay, so we have a title on the top of the graph. Each of the wedges labeled, how many are in each category, and then the final coup de grace is the angles. By the way, the reason I'm telling you put this part in, it protects you if your graph's a little off. Okay? So if your wedges really are sort of out of whack, as long as you have the number in there, I can, and you've done your best to try to get it reasonably close, I can sort of give you credit for it. Okay? So this is sort of truth in advertising and consumer beware and that kind of stuff. So what I'm trying to do is tell you how to get the most points for this. Okay? Everybody cool with this? The steps? All right. Snow accumulations. We're tracked for 10 hours. And there they are. Graph it with the most appropriate graph. Well, as we said before, the most appropriate graph to get time data is a time series, right? Which is basically a line graph, not a line plot, but a line graph. So what we do is we put the time along the x-axis, 10. We do equal increments, 11, 12, 1, 2. We're going to 7 o'clock, 3, 4, 5, 6, 7. And the snowfall, since the largest snowfall on the chart is 1¼ inches, we're going to do 1 inch here, 2 inches here, and it looks like we've got quarters here, a half and 2 quarters here. So that's how the graph should look in terms of how, notice when we do a scale in the y direction, we want to include the last data point and a little bit extra. So we want to have a little margin at the top and the bottom. So you wouldn't stop at 1 1/4, you'd actually go up to 2. Sort of like if you were taking a picture of somebody's face, you wouldn't just go to the very top of their head. You would try to put a little bit of background so you can see where their head ends. A little perspective, okay? How's my timing? Am I going too fast, too slow, just right? Too fast? Too slow? Just right? Okay. All right. 10 o'clock. 10 o'clock, it's 1 inch of snow. I'm going to put a big red circle there. Not too complicated from here on out. We're going to have to label these axes in just a second. But we got 1 1/4 for 11, 1 for noon, a half for 1 o'clock, another half for 2 o'clock, a quarter for 3 o'clock, another quarter for 3 o'clock, a tenth, okay, it's all the way down here, a half, all the way down here, and then 0 at the end, okay? Notice when I get done graphing this, I connect the dots, especially with a time chart, time series, okay? I'm going to put in, some people would put this last line in up from 0. I would just leave it out because we don't know what was happening at 10 o'clock. So I would actually start it with the first data point, okay? And along here, what's along the x-axis? Time. You can put in hours, but time is fine. And then this is snowfall. And since I've got the units listed here, that's fine. And this is a snowstorm data. When you're done graphing time data, you should be able to tell the story of what's going on, right? What happens in this snowstorm? Yeah, if we're tracking the storm, it was still building up, but at 11 o'clock it sort of hit its peak, and then it slowly sort of tapered off, eventually stopping at 7 o'clock. So you should be able to tell the story when you're all done in a well-constructed graph of exactly what happened with this snowstorm. Okay? Any questions about number 8? Okay. 7. Number 8. We have an NBA forward. And that forward is playing basketball, plays 10 games. I want to do the 5-number summary. The 5-number summary. So help me with this 5-number summary. What does the 5-number summary mean anyway? Can somebody help me with, what does it mean? What is a 5-number summary? Do you remember? Do you remember what a 5-number summary is? It starts with a minimum.
Ends with a max.
Ends with the max. Has the what's that? Q1, median, so it's all the quartiles, right? It's like the minimum. So the 5-number summary starts at the minimum. It goes to the max. The middle score is the median. And then in between here is Q1 and Q3. So actually it's sort of where we begin. First quartile, second quartile, third quartile, fourth quartile. And we call this the max, the min, and the median. Okay? So for these scores, let me pop this down just a little bit so we can see it.
Are we going to do the actual little chart, please?
Yeah. Oh, I didn't add the box plot here, so yeah, that's a good question. Okay, great, thank you. So the minimum. To help you do this, I would recommend starting off by putting them in order from smallest to largest. What's the smallest one there?
8.
8. What's next?
12.
12.
13.
13.
14.
14,
15.
15,
15.
another 15,
18.
18,
19.
19,
20.
20,
22.
22, 2, 4, 6, 8, 10. So we had 10 numbers. Okay, we're all good to go. All right. Some of this is a little bit easier than others. What's the minimum score? 8. So I'm going to take 8 and put it in here for the minimum. Right? What's the maximum score?
22.
22. All right, we're going to do the median. I'm just going to count from the ends, right? Fifth, 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 fifth. Okay? Are we cool with that? So you just go from, sometimes I cross them out, like students like to do that. I want you to be able to see the numbers when we're all done. So I just do check marks. But the bottom line is the two center numbers are 15. So what's the median?
15.
15. All right. Q1. Somebody tell me how I do Q1 now.
Same thing you did for the median, except for those 5 numbers.
So I'm going to do median for this left side, right? Same thing again. So let me take away my check marks. I'm going to go fifth, 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 fifth. 13 is the Q1, right? Going to do fifth, 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 fifth. 19 is Q3. Is everybody cool with that? Okay. Now, if I was asked to do a box plot, I would actually start from wherever I want to be able to show the minimum. So I'm going to go 5, 10, 15, 20, 25. Notice I'm doing equal increments in a right scale. For a lot of students, what they'll do is they'll just put 8 at the first point, 13 at the second. That's not correct because it's not drawing the scale. The idea is to draw a scale that's equal. So this, in other words, this region is just as big as this, is just as big, because it matters where these vertical lines are going to go. That tells us part of the graph. Okay. So some people that really don't understand box plots, they always get the same graph every time because the first number is 8, the second number is 13. They're not getting the concept that a scale has to be on here. Okay, an equal scale, and then we're going to put these vertical lines where they belong. And they almost never line up perfectly with these numbers. Okay, so over here are scores. Okay, what am I going to do next?
Put a dot.
What's that?
Put a dot.
Now we're going to do vertical line at what? At each of these numbers, right? Okay, so we're going to do 1 at 8. A vertical line at 8. You have to estimate it. We have to estimate another one at 13. Another one at 15. Another one at 19. And then another one at 22. We connect in middle 3. And then we do the whiskers.
Graph is that?
This is a box plot. Okay? So, in a box plot, when we see a section of the plot that's kind of scrunched together, what does that tell me? Is it Manhattan or is it Kansas? Okay, if I have a quarter of the population scrunched in a little section, are we in Manhattan or are we in Kansas? Manhattan. If you've never been to Kansas, Manhattan is like everybody's on top of each other. Kansas is like you go for miles and miles without seeing a person. Okay, so this is Manhattan. Okay, everything's clumped together. This is Kansas. Okay, it's all spread out. So we can tell right from looking at the box plot that a lot of the data is captured between Q1 and the median. Okay, so right in here between Q1 and the median, We've got 13, 14, 15, 15. A lot of the data is right in here. Okay? There's some spread out over here. There's some spread out over here. But this is where the big clump of data is. Okay? And the last thing we do is label these so everybody knows. Again, this is protection for you in case your graph is not absolutely perfect. When you put this in, everybody who reads it knows that you meant a 19 there, and this you meant that to be a 22. Okay? So we just label it at the end. Are we cool? All right, that's 8. I don't think we have a 9, but let's go to 10. Find the mean, median, and mode for this forward. Okay? The mean, you add them up and divide it by 10. Very cool. 10 is an easy number to divide by. So what did you get for that mean? 15.6? 14.6? 15.6. So the mean, just add them up, divide it by 10, and you get 15.6. No problem, right? The median, we already calculated the median. What's the median? The median's 15. And the mode, do we have a mode?
15.
The mode is actually 15 as well. The most common score, most frequent score is 15. You cool with that? That's the mean, median, and mode for this one. Now we have to come up with the standard deviation. Okay, you remember how the standard deviation calculation goes. What columns did we have for the standard deviation? We had the score. Then what did we have? We had the score minus the mean, which is the deviation. Okay, and then we had the score minus the mean, what? Squared. We're going to add that up, and we're going to remember if we have to divide by n or n minus 1. Okay? When we're all done, and take the square root. All right, so let's write the data points here. Might as well go in order. That'll make life simpler. 9, or 8, 12, 13, 14, 15, 15, 18, 19, 20, 22. Okay? Hopefully this brings back memories. The mean is actually 15.6. So when we're less than the mean, 8 minus 15.6, who has their graphing calculator or their cell phone? 8 minus 15.6 is what? Negative 7.6. Okay? When we take 12 minus that, that is negative 3.6, right? When we take 13 minus that, we get negative 2.6. When we get 14 minus that, it's negative 1.6. And then 15 minus that is negative 0.6. Okay? You can check all these with your calculator, but I'm actually going right down the scale. Every time I get closer to the mean, I'm trimming a point off. Okay, so when I started at 7.6 and went to the next one to 12, I trimmed off 4 units, and then I trimmed off another one, I trimmed off another one, trimmed off another one, and I'm within 0.6 of the mean. When we get on the other side, 18, you have no idea what I'm talking about, just calculate it, okay? 18 minus 15.6, 2.4. Okay, so this is going to be 3.4, this is going to be 4.4, and this is going to be 6.4. For the same reason, I keep increasing, and it moves me away from the mean 1 more unit each time. Okay, is everybody cool with this so far? Then we square it, so now we're burning up our cell phone battery. Okay, a little bit, getting a little workout here. 7.6 squared is what? 57.8. 3.6 squared is? 13 even?
Yeah, it's like 13.
Okay. 2.6 squared?
6.8.
6.8.
Well, it's the other one is 12.94. So I just.
It's 13.0. Okay. 1.6?
0.37.
No, this one. 1.6.
Oh, 2.6.
2.6. The next one is 0.36 or 0.4. We'll round it off to round them all off to the same. So 0.4, 0.4, 2.4 squared,
5.8.
5.8. 5.8. 3.4 squared,
11.4.
11.6. 4.4 squared,
19.4.
19.4. And 6.4.
41.
41 even. 0.0. Okay. So once we do all that, so it's not complicated, it's just a lot of work. Okay, each one of these is a deviation, then we square them. So we have to have just the patience of working through this. We total it, and what do we get for the sum of the deviations squared?
158.7.
158.7. Okay, and now we're getting close to writing the final formula. What was the final formula? It was the square root of the sum of the differences of the deviations squared all over, is it n or n minus 1? N, okay. So we have the square root of 158.7 divided by 10. We get the square root of 15.9. And then that works out to, that's just the shy of 16. So it's going to be about 4, right? So we got a standard deviation of about 4, approximately 4. Okay? So there's nothing really complicated there. It's just a tedious calculation. I like teaching you with the columns so you can, all you do is keep calculating within the columns. Let me review it one more time so we've got it. You've got the scores in the first column. You simply take them from the mean, subtract the mean from it, and get this number. The negatives and positives are all important, but they're not absolutely critical because we're going to square it anyway. The most important thing is you get these numbers right, okay? So 8 minus 15 is 7.6. Just with your calculator, do that center. The nice thing is when you're right here, if you got a squared key on your calculator, you just hit that squared key and you're right here, okay? And just go down. It's tedious. Total it all. Then put it underneath the radical. Divide it by n, 10, and then take the square root and you're at an average of, a standard deviation of 4. We cool with that? I have to do that one sort of nasty calculation. Not that you're ever going to teach third graders the standard deviation, but that's part of the course. So apologize for how tedious that is. But if you have some notes, it's actually not so bad. Is everybody cool with this? All right. Let's go to 12. The key word in number 12 is what percentage of a random test group. So when I say random, that means it's going to be typical of sort of national averages. There's not going to be any biases or anything. So what the averages that we would normally see nationwide, we would see in this random sample, if it's truly random. Okay, so we're at 12, and it says, what percentage of a random test group, bless you, would you expect to have an IQ of less than 85? So the first thing that I do, and you don't have to do it this way, but the first thing I do is I draw a picture. Once I have a picture, then I can actually picture where everything is. It's the IQ test, and as we covered in class, the IQ test has an average or a mean of 100. It has a standard deviation of 15. So if I were actually working out this problem and you were looking over my shoulder and looking at my paper, you would see a little bell curve, 100, 15 off to the side, and that tells me the average is 100, and the width, the standard deviation is 15. Okay? Now, I know that I've got these wedges, and that first wedge, how much data should be between the mean and that first wedge? This one over here. So this first wedge is going to be 85, right? How much data should be here? 34%, right? Remember we had 68 between 1 standard deviation below and 1 standard deviation above. So each one of these should have about 34% in it. Okay? Now, the next thing I do is actually shade in the area they're asking me about. Okay? They're saying the IQ of less than 85. Is it going to be to the left of this number or to the right of the number?
Left.
Left. And their key is the numbers are getting bigger as you're going to the right. So I'm going to want all the numbers less than 85. It's over here, right? Okay. Well, you can do it a variety of different ways, but if this is half the curve, that's 50%. And this is another 34%, that's 84%. So how much is left in this tail? 16%. Okay? Or another way to look at it is, this half of the curve is 50%, 34 is over here, so the rest of it has to be 16. But it's the same logic either way. Okay? So when you get to project 1, the first question is going to be sort of one of these even, one of these even benchmarks that come right at where the standard deviation is. Okay? So we can use that table, and remember how the graph worked. The percentages, they're actually in the book. The first group from 1 standard deviation to the left to 1 standard deviation to the right is how many, what percentage? 68%. 2 standard deviations is what? 95%. 3 standard deviations is 99.7%. So there's a chart in the book if you forget that, but that should be able to give you, if you do a little reasoning, you should be able to figure out each of the sizes of the wedges. Okay, this I think is 34. This is like 13 and change, and so this is like 2.3, and then a teeny little bit on the other two ones. Okay, number 13. A college wants a special reading class for students who test below 380 on the reading portion of the SAT. If the school is expecting to admit 800 students, and these students seem to follow the national testing pattern, how many of these students would you expect to be placed in this special section? Okay, so let's begin with drawing a picture. Since it's national reading SAT, what's the average? We were doing SAT data. Remember what the average was? 500. Okay, so the mean is 500. The standard deviation is what? 100. Okay? So if this student is testing below we want to know the group that's testing below 380. I realize it's not even, right? 400 would be 1 standard deviation, and 300 would be the next one. So it's in between. It's a tweener. Okay? If it's a tweener, I've actually got to use something like a table, but I showed you how to do Excel. Excel will give me the proportion that's to the left of a score. So I've got to put in the score. The score actually is 380. I've got to put in the mean. That's what? 500 is the mean. And I've got to put the standard deviation. And what's the standard deviation? 100. Okay? So when I go to norm dist, that was the first one, right? I'm going to go to norm dist. And, there's my good way to do it. Yes. And let me put the screen down so you can see what I'm doing. So the score we said was 380. The mean was 500. And the standard deviation was 100, right? So how do I get the score of 380 that was given in the problem? How do I get the mean? I know it's standard, it's the 150. Okay. So we know the score is 380. We know the mean is 500. We know the standard deviation is 100. The mean comes from the fact that it's the reading SAT, and the standard deviation comes from the fact that it's the SAT. And now I'm going to do norm dist. So I go to my little function wizard, or I can insert a function either way. If you find there are apps on the computer that you can actually do the same kind of calculations, in case you don't want to use Excel. But Excel is just everywhere in all the labs, so that's why I use it. And you type in norm dist. I actually have it below, but the first time in, you're going to type in norm dist, hit go, find norm dist, and you can tell you're on the right app or right function when it says, okay, what's the score? Oh, I know that. It's 380. What's the mean? I know that. That's 500. So if a window comes up and you don't know any of the choices, it might tell you you're in the wrong function. So 380 is the score. 500 is the mean. The standard deviation is 100. We always put true for the fourth one. It's a quirk of Excel, what can I say? And then we click on OK. So the area to the left of the curve, to the left is 380. So we've got mean is 500. Standard deviation is 100. This is 380. Okay. The area to the left of it is 11%, or 0.11507. Okay. Now, if I have 800 students, and I want to figure out how many students this actually is, or this actually corresponds to, I've got to actually take that proportion and multiply it by 800, right? Okay. So I'm going to take the proportion that's to the left of that point. It's a little less than, a little bit more than 10%. So if we had to estimate it, we'd say it's about 80 students, maybe 88 students. But we can actually calculate the exact number by taking 0.11507 times 800, and what do we get?
92.1.
92.1. Okay, so a little bit more than 88 is fine. Okay, and so since these are students, we would round this off to 92 students. So our prediction is there will be 92 students in that first band. Okay? Is this making sense? Yeah, kind of. Okay. All right. The second question for the last question is, a college wants to give scholarships to the top 10% of students on the math SAT. Okay? So, can I erase this? Does everybody have this copy? Okay. Top 10%. That's these guys up here. Now we kind of have to work backwards through the process. If there's 10% above this number, so this top 10%, what percent is below this number? Remember that Excel always calculates to the left, because those are going to give us the number under it. So we're going to actually put in 0.90, or 90%. Okay? We're going to use the other one, which is norm in. That's when you know the percent, and you want to find the score. So if you know the percent or the number of students, and you want to find the score, it's sort of working backwards through norm dist. So if the final answer is what's the score, a college wants to give scholarships for students scoring in the top 10% on the math SAT. What should be the cutoff for the test? That's a score. What score on the SAT should students get to have this scholarship? Okay? So we're going to go to norm in. We're going to put in the proportion. Now it's 0.90. That's 90% of the students are testing below that cutoff. Okay? The mean is going to be what?
500.
500. Why?
National average.
It's the math SAT, just like the reading SAT. And then the standard deviation is 100. These are all the same. So for SAT data, the mean is 500, the standard deviation is 100. For IQ data, the mean is 100 and the standard deviation is 15. Okay? So we're going to go to norm M. Let me bring up Excel one more time. I'll just jump over here. Now we have the proportion for probability, and that is 0.90. We have the mean. It's still 500, even though it's a different section of the test. All of them are scaled, in theory, to be 500 for a mean and standard deviation of 100. Now I'm going to use the other one, norm inverse of norm. Okay, it's his cousin that does everything backwards. You probably have cousins like that. Okay. So norm in, we type it in, N-O-R-I-N-D. Norm in is the first one. Notice it says, what's the probability? That's 0.90. What's the mean? 500. What's the standard deviation? 100. So when it comes back, the actual score is 628 on the SAT. Since you can't get a 628 on the SAT, what's this cutoff going to actually be? 630. Anybody that gets 630 or more is going to get this special, in math, is going to get this special scholarship because they're in the top 10% of people taking the SAT in math. Okay? So we look at the difference. If I know the score and I'm trying to find sort of the proportion of students, I'm going to use norm dist. If I know the proportion of students or probability and I'm looking for a cutoff and I know the mean and standard deviation, I'm looking at norm in. Okay. Just want to wrap up a couple of thoughts because we're almost done. I think some of you have been done for a little bit. Okay? This is a little intense. First of all, I have to make some apologies. Apologize that I didn't have this posted earlier so that you could work on it, and I didn't make it clear enough that I wanted you to sort of go over it before we came to class so that you had everything worked out so that this would be more of a review than seeing it for the first time. So for a lot of you, this is the first time you saw it, and I take ownership for that. It's my fault. So this is what I want to do. On Thursday, I was planning on giving it to you today and letting you work over the next couple days on it. Okay. What I'm going to do is actually give you project. I'm going to post it a little bit before class next time. I'm going to let you work on it on Thursday in class. Okay. And then take it home over the weekend and bring it back on Tuesday. Okay. So apologize for not having my act as close together as I would have liked. Sorry for the enduring of this whole review today. I know I put some of you to sleep. I did get a couple young. Thursday we'll come back. I'm going to give you project 1. You can start in your groups here and then finish them over the weekend. Okay? Have a great couple days and I'll see you on Thursday. Yep.